So hello there and welcome to another tutorial. My name is Tanmay Bakshi and today we're going to be going over how you can implement and optimize a proof of work algorithm on GPU using CUDA. Now this is really interesting because we're going to go from just being able to process a few hundred million hashes per second on CPU to now being able to process over 8 billion hashes per second on 4 NVIDIA Tesla V100 GPUs. Now before we get deeper into this whole proof of work stuff, there's one more thing that I want to say. Today we are going to be taking a look at what are known as CUDA kernels. So writing code that's going to run on your GPU to run, again, what's known as an embarrassingly parallel task. That's the technical term. So if you'd like to learn about the fundamentals of CUDA kernels and how they work, there is a YouTube video that I recorded a couple of years ago on the world of CUDA and the basics of how you can implement some simple vector mathematics on CUDA chips. But today, we're going to be taking those concepts and scaling them even further. So there is a link on screen right now where you can go ahead and take a look at that previous tutorial if you'd like to find out the fundamentals of CUDA kernels.
So hello there and welcome to another tutorial. My name is Tanmay Bakshi and this time we're going to be going over how you can use CUDA C for general purpose GPU computing.
And of course, if you'd like to be notified whenever I release new content like this one, please do feel free to subscribe to the channel, ring the notification bell, and that way you'll know when I release a new video on a topic just like this one. Now this is absolutely fascinating stuff. And what do these numbers mean? Well, first of all, we'd have to understand what a proof of work algorithm really is. Now, a proof of work algorithm on its own doesn't really mean much. It's just an algorithm where you're trying to brute force a certain hash condition. However, when you apply this proof of work to another algorithm, like for example, the blockchain network, then you get something that's really useful. By using the proof of work technique, blockchains can actually verify transactions in a completely decentralized way, meaning there's no centralized server where all those transactions are stored. This is really interesting stuff, but again, what does proof of work actually mean? Well, let's take a look. First of all, it's important to understand the concept of a hash function. I won't get deep into exactly how they work, but there's a series of hash functions called the SHA functions. There's SHA-1, 2, and 3. SHA-2 in specific was developed by the CIA, and it's what's known as a cryptographically secure hashing function. So what that means is we can feed in as much data as we like into SHA-2, and it's going to output a series of bytes. And these bytes are what's known as a digest of the information that was fed in. Now, the length of those bytes is limited. So for example, SHA-256, which is the most popular hashing algorithm under the SHA family, will output 256 bits of info, or 32 bytes of info. Now here's the thing about SHA-256. Because we can only represent 2 to the power 256 total possible hashes, it's always possible that two completely separate inputs will end up having the same hash. But the likelihood of that is exorbitantly small. It's essentially infinitesimal, because of course we have 2 to the power 256 possible hashes. I mean, if you were to feed in a couple million bytes, and even just one of them changed slightly by a single bit, you would most likely get a completely different hash. The entire idea of a hashing algorithm is that you cannot go from output to input, only input to output. Now, paradoxically, in a way, a hashing algorithm is more cryptographically secure if it takes longer to compute. Because if it takes longer to compute, then it's harder to brute force that algorithm. But with cryptocurrency mining, people have come up with all sorts of creative ways to get really, really fast hashers in order to gain as much crypto as possible. Like, for example, ASICs that I'm sure you've heard about. But today, what we're going to be doing is quite interesting. We're going to take an input string. So for example, Tanmay Bakshi. And we're going to try and find a sequence of 20 characters that, when appended to the input string, in total result in a SHA-256 hash where the first n number of bytes are totally zeros. And so, for example, maybe we want to find a certain sequence of 20 characters where when you take the input and append it, the first 3 bytes of the hash are all zeros. Now, you might think, why would you want to do that? Well, you don't really need to do that for anything, but what that proves is that your computer has done the work to find those zeros, and thereby in a blockchain, you could use that work in order to prove that you verified a certain number of transactions. And so that is how blockchain technology works. And today, we're going to be taking a look at how you can implement that proof of work algorithm. Now, hashing is something that's very embarrassingly parallel, is what the technical term is. What that means is, we can spin up thousands of threads on a certain machine that are all working to just generate random strings, hash, and check if it meets the condition. Because there's no logic involved. You can't reverse engineer a hashing function. The entire assumption of a hashing function is that you can't do that reverse engineering. And so we have to essentially generate random strings and brute force check potentially trillions of hashes in order to find the right one. And so, on CPU, this can be difficult, because even the top of the line 128 thread IBM power servers can only process about 100 million hashes per second. In fact, if you want to take a look at how I actually implemented a CPU-based version of this, do take a look at the live stream that I held on Wednesday, June 17, in order to implement a CPU-based hasher. It was a live stream, so you can actually take a look at the whole process of how we went through the idea of architecting and implementing that CPU-based hasher in Golang and now in C as well. However, we cannot make do with only a couple 100 million hashes per second. We've got to go even faster, which is why we're going to be implementing on GPU for about 8 billion hashes per second. Now that's even then a little bit slow, because then with crypto mining you want in the trillions or quadrillions per second, if you want to earn any money. But for an application like this one, under the constraints that we have for our solution, it's absolutely more than enough. Now, in case you're into this sort of stuff, when I actually ran the CUDA profiler to figure out how fast the solution is, the compute speed of light score for this application was approximately 75. So I am actually using a lot of the compute on the GPU, and I've tried to minimize the overhead as much as possible, enabling as few memory writes and reads as possible, enabling as much data to be stored in GPU registers, all these sorts of really intense optimizations to get to 8 billion hashes per second. And now I would love to show you exactly how those CUDA kernels work and how you can build them for yourself. And so without any further ado, let's go ahead and take a look at how you can implement this on an IBM power server with 4 Tesla V100 GPUs in a totally scalable way. It works on multiple GPUs. You can just tell it how many GPUs you want to run on, and all these other sorts of hyperparameters. So let's take a look at how you can implement proof of work on CUDA.
Alright, so now let's get started with taking a look at how the implementation of this proof of work algorithm works on CUDA. Now, as you can see, I've already SSH'd into a server. This is a power server, so it's using an IBM Power architecture, not x86. So what's incredible about CUDA is that, of course, it is completely cross-platform. It even works on IBM Power servers. In fact, it's better on Power servers because of NVLink enabling really, really great memory bandwidth, enabling the CPU and GPU to talk super quickly. Now, that doesn't really play into this use case in specific. However, for deep neural networks and these sorts of things, Power is great. Now, as you can see on me over here, I've got 4 NVIDIA Tesla V100 GPUs. These GPUs are not being used at all currently. They're completely free to use, and what that means is that there's nothing else running on them. So we're only going to be running the proof of work algorithm. I have also gone into my home folder, into a folder called redesign train, which is just the name that GitHub assigned this Git repository. If you take a look, this is a GitHub. This is a Git repo, and so you can find this on the redesign train repo on GitHub, link of course in the description. Now, the way this works, there are a couple different files here. You don't need to worry about a.out right now. All you need to worry about is the new.cu and SHA-256.cuh files. The new.cu file is the main file that we want to care about. I guess new.cu could be like a main.c file, and SHA-256.cuh would be a main.h or just a header file that we want to include. Now, this header file is doing more than a traditional header file. It actually has essentially all of the code for the SHA-256 algorithm, and this runs on the actual GPU. So these are device functions. A device function is a function that runs on the GPU. Once again, CUDA has very C-like syntax. In fact, it uses C compilers in the back end. And so that's the SHA-256 implementation. I did not write that SHA-256 implementation from scratch. I modified it to fit this use case, and I will be linking to the original implementation in the description as well. But now, let's go ahead and dive right into new.cu. Now, essentially, what I want to start off by doing is describing the high-level architecture of the program, because I feel like that's a lot more important than the nitty-gritty of how exactly everything communicates. So let's go ahead and start off with the high-level architecture. Now remember, GPUs are fast. Individually, instruction for instruction, they may be slower than a CPU, but if you can run like thousands of different hash brute forcings per clock cycle, if you can run thousands of them instead of just a couple like you could on a CPU, that means GPUs are fast. In fact, they are so fast that they usually sort of reverse the traditional bottleneck. Usually your bottleneck is in compute, because compute takes a long time. And things like creating data or loading data aren't usually the bottlenecks. However, with GPU compute, that gets turned around on its head. As a matter of fact, the GPUs are so fast that it actually takes us longer to generate the random strings and feed them to the GPUs than it does for the GPUs to process those random strings. Especially because you can't just feed it a single random string and expect it to finish things really quickly. You have to feed it entire blocks of random strings super fast. And so unlike on the CPU implementation, I don't have a separate random number generator and a separate GPU checker. Instead, what I do is I have a single CUDA kernel that will take a random seed, use that random seed to generate random strings, and at the same time check whether or not those random strings actually match our condition. That way we save out on two bottlenecks. First of all, generating on CPU is slow compared to what the GPU needs to feed it to full efficiency. Second, we don't need to generate all of those strings on CPU and then copy that entire block of memory over to GPU, over PCIe. Instead, what we can do is we can simply generate and use it on the GPU. That way we don't even need to have a block of memory for this stuff. We can just keep it entirely in registers. So it's really fun stuff that we can do if we're able to do it directly within the single kernel. That's why I've merged it all into a single function. But now, I know what you're thinking. How exactly does this work? So let's get into that. Now, first of all, of course, after my traditional imports, I've got a couple of definitions over here. And I want to quickly go through those definitions. So I start off by defining the text. So this is the prefix that we want to feed into the actual program so that we can find some text that when appended to this text, the result gives us a SHA-256 hash that starts with a certain number of zeros. I'm also just having to define, we're working with C, so I have to define things like how long the text is. I got to define how many, and this is the sort of GPU part, these three variables over here. I've got to define how many threads I want the GPU to execute. I want to define how many blocks of these threads the GPU is going to execute. And I want to define how many GPUs I want to use in total. So the way this works, and this is a little interesting, the way CUDA wraps its compute. With CUDA, you don't just have n number of threads. You have n number of blocks, each block containing n number of threads. And so it's interesting the way that happens in different use cases. You want to have different arrangements of blocks to threads. You can specify that. There's of course limitations, and it really depends on things like the warp size of your GPU. But in this case, I've found 1500-256 to be a good combination for this GPU in this use case. And so you want to really specify this to what it is that you are doing. Although this is a pretty good standard set, is what I would say. Now, of course, the way this code works, and this is the fun part, is that the GPUs, that this implementation that I've created actually supports multiple GPUs. And so what that means is you could have a machine with 10 different GPUs on it, and you could just say, I want to run on 10 GPUs, and the rest of the program will automatically fit to run on 10 GPUs, or even just one. But this case, I've got 4 GPUs. Now, I also want to specify the difficulty. So what is the difficulty, you may ask? Well, remember, what we want to do is we want the output of the challenge to say a certain number of zeros that a certain SHA-256 hash should start with. In this case, we want the algorithm to output a SHA-256 hash which starts with 4 consecutive bytes worth of zeros. That's a lot of zeros. So that's 32 zeros that we're asking it to do. In fact, if you see a little bit later in the code, we actually bump that up even further a little bit by a few more bits. So this is a really, really intense challenge, and I can't wait to see what the performance numbers are like. From there, though, I also do go ahead and define the random length. So this is the length, the maximum, the actual length of the number of bytes that we want to append to the text to come up with the hash. Now from there, I just have a pretty simple function called constant called character set. This is the set from which we can actually choose a random letter or a random character to insert into our solution. And so we can, of course, add more characters to this if we want. We can remove it, doesn't really matter. In this case, just to keep it readable, I decided to have a pretty standard set of characters. And from there, I've got a function, and this is where the fun starts. This is a device function called device random gen. Device random gen, what it does is a pseudo random generation function that takes an unsigned long, so an unsigned 64-bit integer, and it does a bunch of bit operations, bit shifts, things like that, and it's going to try and essentially create a random number. Now, you can't really create a random number with computers as they are today. That's not how they work. That's impossible. But what you can do is you can make a function such that the input, even if it changes very, very slightly, the output changes a lot. And that's how random number generators work in computers today. And this is an implementation of a super rudimentary random number generation function. Now, if we wanted things like being able to be cryptographically secure, we wouldn't be using this random generation algorithm. But if you think about it, we don't need to be cryptographically secure. We just want a random number function that's relatively uniform with the input that we give it, or the bounds that we give it. This is quite uniform, and so we don't need to go more advanced. In fact, the simpler this function is, the more CPU or GPU clock cycles we can shave off. That adds up to millions of cycles, many seconds of compute, which are really valuable here. So just a super simple random number generation function. Now from there, I'm going to go ahead and skip this function for now. I'll tell you what it does and we'll come back to it. Basically, this is the CUDA kernel. The CUDA kernel that is responsible for taking the input text. It's taking a pointer to where to store a solution if it finds a solution. It's taking a pointer to a variable where it will store a Boolean value of whether or not the kernel has found a solution, as well as the random seed. Now, really quickly, I'm going to say whatever I just said. How does that sort of relate to the function parameters? Let's take a look. So as you can see, this over here is the string or the byte pointer to the prefix that we want to append to. There's also the byte pointer to the solution, which is by default a null pointer. However, not a null pointer per se, but it's not initialized memory. What's going to happen is if this CUDA kernel finds a solution to the problem, it'll put the solution into this pointer, or where this pointer points, as well as just an integer or a Boolean value. By default, this is -1, and what we want to do is set this to 1 if the CUDA kernel finds a solution. So that way the CPU knows if we actually have a solution. And of course, as I mentioned, the basic random number generator seed. Now we'll come back to this function in just a moment, but first I want to go ahead, as I mentioned, we want to have super simple random number generation, so I also have a version of that same function for the host, for the CPU. That'll be compiled to CPU assembly, not GPU. I also just have a little pre-SHA-256 function. This is mostly a legacy carryover from the previous code base that I'm going to link to in the code base, link to in the description. There's definitely a much better way to do this. You could literally just put __ constant as a prefix for the variable. But anyhow, this is a legacy carryover which can be removed in a later commit. From there, I also have a long called time milliseconds. This is going to return the current time in milliseconds. That way I can actually go ahead and time things like execution and figure out how many hashes we're processing per second. From there, this is where the sort of CPU-GPU interconnect comes in. we start off by defining a structure called handler input. What is handler input? Well, the way this implementation works is, of course, there's the main thread, and that's the thread that the program is launched from. The main thread actually spawns a bunch of different threads. Specifically, however, it'll spawn n number of threads where n is the number of GPUs that you want to execute on. So if you only have a single GPU, it'll spawn a single thread. If you've got 10, it'll spawn 10 threads. Now, each thread is responsible for handling the input-output for a single GPU. And, of course, as the handler, it needs to have some sort of input to tell it what to do. So this is the handler input structure. It tells each handler thread information about what it needs to do and how it needs to do it. In this case, the only things that it needs to know would be, first of all, the device. So what device exactly are we using? Are we using the first GPU, the second, the fourth, the 10th? What are we using for this specific thread? But also, within the handler input, I want to store an unsigned long called hashes processed. That way, whenever the worker actually processes, say, n number of hashes, I can go ahead and store that here and say, I've processed these many more hashes. And the main thread can continuously look at that pointer and always be like, all right, you're incrementing the number of hashes you process. You don't need to do this. In a real life scenario, you probably wouldn't. But this is for benchmarking. This is so that we know how many hashes we're processing per second. And you'll be pretty surprised when I actually run this code just how fast it is. But anyhow, from there, I also just have two more global variables. One is the solution lock. And so this is a mutex that makes it so that the main thread knows when a worker has found a solution, as well as a global pointer to solution. Now, basically, this is the chunk of CPU memory that will actually contain the solution if we find one. Hopefully we do. Now, this function over here, this absolute unit, is going to be responsible for actually launching and sort of maintaining the GPU handler thread. It takes a void pointer, so a raw pointer, and that void pointer is then casted to a handler input pointer. And so that enables us to know what the input is. Now, the first thing we got to do right off the bat, before we even begin, is take the device that handler is responsible for handling and tell CUDA that this thread intends to work with that device so that we can get a context that tells us that we're only working with that device. So the first thing we got to do, set device. That's the most important part. Then the rest follows. First of all, what we're doing is, of course, that legacy carryover I was talking about, pre-SHA-256, set up the GPU memory a little bit. From there, what I do is essentially just allocate blocks of CPU and corresponding GPU memory and sync them so that we know what we're doing. Now, CUDA has some fancy new features that enable things like, for example, being able to access GPU memory from the CPU implicitly. But the thing is that introduces very, very little overhead, but it's overhead nonetheless. And the entire point of this application is to be as blazingly fast as possible. So I'm not using those fancy new convenient techniques. We're still going the old-fashioned way. And that old-fashioned way is I go ahead and create, first of all, the CPU prefix, right? So I go ahead and get the text that we're looking for. Put that into a pointer, and I go ahead and also allocate memory for that, space for that on the GPU. So I get a byte pointer, but this isn't like a traditional C pointer. This is a CUDA mallocked C pointer. This is owned by the GPU, and so that's something to keep in mind. Then what I do is a simple CUDA memory copy. So I copy the CPU prefix over to the device. And this is a host-to-device transfer, host being CPU, device being GPU. Then I go ahead and allocate memory for the actual solution if and when we find it. Again, there's no guarantee we will, but if we do, we want to have memory to actually store it. I then go ahead and allocate the same memory for the device. No syncing is required here because that comes later. Then finally, I also just allocate the memory for the block contains solution variable, which, I mean, even an integer needs to be allocated with CUDA. You couldn't just say, you know, int block contains solution equals -1 and then pass a pointer, because you want to specifically do a CUDA malloc. So it's pretty interesting there. But then again, I just copy the device version to the CUDA version because the device version is set to -1, and we also want the CUDA version to be set to -1. Now after that, I just go ahead and get a random number generator seed, which by default is equal to the time in milliseconds. And then after that, we go ahead and start handling the GPU because we've got all of our basic stuff figured out. Now, the way this is going to work is we start off by actually taking the host random number generator function and feeding the time in milliseconds to that function so we can modify it, so we can mutate it across every iteration. Because, of course, every iteration, when we call the GPU, we don't want to be using the same random seed. We would be doing literally nothing. And so we go ahead and pass it the random seed, make it modify. And then what I go ahead and do is take the number of threads per block, take the number of blocks, multiply to figure out how many hashes the GPU is about to process. I then go ahead and add those to the total number of hashes processed. Once that's done, now the main thread knows that we're processing hashes, right? Not exactly important, but it's good for benchmarking. Then I go ahead and do something called a CUDA kernel invocation. The CUDA kernel invocation is going to look like a function call, but it has this weird thing in the middle. And this weird thing is telling CUDA how many threads and how many blocks we want to execute on. So it's telling it the topology of the execution. Once we've done that, we want to pass it the device prefix, the device solution, the device whether or not contains a solution, and the random number generator seed. So I know that's a mouthful, but I've already described these parameters. The 4 of these parameters are responsible for, telling the GPU what to do and getting a result once the GPU actually has a result to give us. Then I go ahead and run a function called CUDA device synchronize. So this is kind of like pthread join for CPU, but for GPU instead. Except this is going to wait for any non-blocking operations. It's going to block until they're all done. This includes CUDA kernels, this includes CUDA memory copies, this includes anything that's non-blocking. This will block it for you. And so this is there so that we can actually wait for the kernel to finish executing. Once that's done, then I execute only a single and a very small memory copy every iteration. Only a single memory copy. So we're trying to reduce bottlenecks here. And that memory copy is going to copy the Boolean of whether or not a block contains a solution from GPU memory to CPU memory. Once that's done, then we're going to check if it's equal to 1. So did the GPU find a solution in this iteration? If it did, then we're going to do a bit more of an expensive memory copy, which will copy the actual solution over from GPU memory to CPU memory. We're going to assign that solution to the global variable, and then we're going to unlock the solution lock. So what's going to happen is, in the beginning, the main thread is going to lock the solution lock. It's going to launch the threads, and it's going to attempt to lock it again. Now, when it comes to lock the solution lock for a second time, it's going to block the main thread. It's going to block because, well, we don't have a solution. And so what's going to happen is, when a handler thread actually finds a solution, it's going to unlock the solution lock, which means the main thread can now lock it again, and it's done blocking, it can continue, it can actually print out the solution. So it's an interesting way. I wanted to use semaphores, but the problem was that for some reason on Mac, semaphores wouldn't block, which almost seems like a bug, but regardless, I'm using a mutex instead, and it works just as well. Then we go ahead and break the loop, do a CUDA device reset, and return null. But I also just quickly check that, hey, if another GPU handler thread's found a solution, then there's no need for me to continue to compute, so I can just break CUDA device reset, return null, we're good to go. And so the way this works is pretty fascinating. And then, of course, we've got the main function. And the main function is basically just going to do a little bit of initialization. We're going to go ahead and initialize the solution lock. As I mentioned, here's the first lock. So this one's easy. It's by default unlocked. Main thread locks it. It's got lock. But then from there, what it's going to do is it's going to initialize 2 arrays. It's going to initialize an array of thread identifiers. So this is so that we know the thread IDs for our handler threads so we can kill them at the end or join with them at the end. And also an array of pointers, so a double pointer. And this array of pointers, each element actually points to the part of the handler input struct that defines the number of hashes that were processed by that GPU. And of course, we're using this so we actually can tell from the main thread how many hashes were processed. Now, I also go ahead and calculate the start time Once again, this is for benchmarking, so we can see, how many seconds it takes for the GPUs to actually do their magic. And then I just loop from 0 to the number of GPUs. I go ahead and create the handler input block of memory. I allocate that. I set the device using the loop index. I go ahead and set the number of hashes that have been processed to 0 by default. I could absolutely use call lock, but that takes a bit of extra overhead. Let's not talk about that right now. And I also go ahead and take a pointer to the part of the structure that defines the hashes that were processed, put it in that first array I was talking about. Then I go ahead and tell pthread to create a thread, and I tell it to put the thread ID directly inside of the array of thread IDs. And I, of course, pass it the handler input. If you take a look here, we are passing it handler input for the thread. I then just go ahead and sleep a little bit, and the reason for the sleep is actually important, because if you launch the threads too quickly and they calculate their time in milliseconds at the same time, they're both going to have the same random seed and the same, further random seeds. And so you're, again, going to be doing nothing, and there's no point of that. So I make sure that I sleep for a little bit so that we have different random seeds. Then what I do is I have an infinite loop, and this is pretty fun logic over here. What I do is I actually go ahead and loop through all of those pointers to the handler input structures, and I go ahead and essentially what I do is I take the values that they point to, so the number of hashes that were processed, get a sum of all the handler input functions, or handler inputs, and then I go ahead and sum them. I take the elapsed time, and I print out in real time how many hashes have been processed, how many seconds have elapsed, and the current hashes per second count. So this is something that's going to continuously update even as we are calculating a solution, even as we're brute forcing a solution. And this is the advantage of having a separate main thread and separate handler threads. Then I just have a little logic that says if we found a solution and it's no longer uninitialized memory, then break the loop, print out a new line so we can separate. Then, just for the sake of safety, lock the solution lock again. That's really important. We don't want to be reading uninitialized memory. So we go ahead and lock it again, and that's only possible after the handler thread is unlocked, meaning the main thread locks it immediately, and we're good to go. I then go ahead and calculate a final elapsed time count. I go ahead and join with all the GPU handler threads, and then from there I just go ahead and calculate finally the number of hashes that were processed, and then I print out the solution. I print out the total number of hashes processed, the time that it took, and the hashes that were processed per second. As you can tell, this is a really fun dance between CPU and GPU and processing on all sorts of different devices. And now that you understand the overall architecture, we can come back to the CUDA kernel that I was promising. Now, the CUDA kernel, remember, is a single function, and this is invoked once per thread. And remember, there are multiple blocks of threads. So this function is actually called thousands of times every time we invoke the CUDA kernel. And in order to know which thread you are in this function, there's a bunch of global or system variables here, like block index, block dimension, and thread index. By leveraging those, you can know which thread you are. And that's important for me because by knowing which thread I am, I can modify my random seed to be different from every other thread's random seed. And therefore, we actually have GPUs doing compute. And not nonsense. And so then what I do is pretty simple stuff. Go ahead and initialize a SHA-256 context, create the digest, and this is a block of 32 bytes, which represents the final SHA-256 hash. Go ahead and create the random bytes, create the random seed, add in the thread index. Then go ahead and generate the random string by looping. Then finally go ahead and initialize the context, update it with the prefix, so go ahead and calculate the SHA-256 for the prefix, calculate the SHA-256 for the random string that you append, and then go ahead and finalize that hash and store it within the digest. Once that's done, we have a little bit of difficulty verification going on, and so all I need to do is just loop through 4 bytes, because we're referring to difficulty, which is referred to as 4. So loop through 4 bytes, make sure they're all 0. If any one isn't 0, just return immediately, right? We know we don't have a solution, just return. But if it did pass that, then we have another test. The other test is, check 4 more bits. So not a whole byte more, just half a byte. So in total, we're looking for 36 bits of zeros to begin with. That's a magic number. It can be really whatever you want it to be. The less, the more easy it is for the algorithm to find a solution. But in this case, it's enough to be challenging, and that's the entire point. In fact, I'm actually going to make this a bit more difficult, right? Let's bump it up a little bit from 36. Then, of course, I go ahead and do a final check. If we've reached this line of code, we know we have a solution on our hands. But if another thread's already found a solution, just return. Don't copy your own memory. And then go ahead and just immediately say, you know what, I found a solution. And then from there, go ahead and copy this thread's solution to the memory that is allocated specifically for the purpose of storing the solution. And with that, we're done. That's all there is to it. I know it seems like, wow, we coded an entire GPU in just that much code, but yeah, we did it, and that's the power of CUDA. That's why we use CUDA over things like OpenCL or Metal. It's just genuinely more intuitive and easy and powerful to get things done with CUDA. Not to say that you can't get things done with OpenCL or Metal or Vulkan or whatever else you want to use, but CUDA has been developed from the very beginning to be great at GPU, and it really shows in the way that we can code with it. So now if I go ahead and exit Vim, we can go ahead and have some fun. So I'm going to go ahead and use NVCC, which is the NVIDIA CUDA compiler, to compile my code. Now I do want to tell NVCC to run full optimizations, like as high as it can get. And these two flags that I pass it are telling it basically, go all out with your optimizations. Don't hold back. Now it doesn't have an O fast flag like Clang and GCC, it just has up till O3, so we're using O3. But now, if you take a look, we have a compiled binary. And watch this. This is so fun. What it's going to do is it's going to start in real time, printing out the number of hashes in total that have been processed, the number of seconds that have elapsed, and the hashes that are being processed per second. Watch this. It takes a few milliseconds to actually initialize, but once it initializes, you can see that it just gets going. Like, take a look at that. Wow. We've already processed, in the amount of time that I said this, over 100 billion hashes. It's processing 8 billion per second and counting. The most that I've seen this peak at is about 8.3 billion per second. That is incredible. And so what we're going to do is let this go. Yes, look at that. 8.2, 8.23, 8.24, 8.25. Of course, there's diminishing returns as you get higher and higher. And the reason for that is one of the reasons, at least, is that, remember, there was that initialization cost in the beginning. And so as you continue to process more and more hashes, you're compounding and you're sort of reducing that initial cost on the number of hashes per second. Oh, wow. We're at 8.36, 8.37. We're going further. We might actually get to 8.4. Now, remember, if your problem is too simple, then it's always possible that you will find a solution so quickly that you will not be processing very many hashes per second because the initialization cost was too high. But, oh, we reached 8.4. This is actually a pretty tough problem for it to solve. Maybe we need to crank down the difficulty a bit. But actually what I want to do is I want to let it go ahead and solve it on its own. We're about to hit 1 trillion hashes in just a moment. So I'm going to go ahead and speed up the video, and we're going to go ahead and wait for a solution to this problem. I'll be right back. Alright, so now let's take a look. As you can see, we processed 1,059,079,680,000 hashes. That is mind-boggling. The fact that we did it in just 2 minutes and 5 seconds. Wow, okay. We found the solution to the problem, which is amazing. And we can see our final hashes per second count over here. Of course, this is slightly lower than it was over here because there was not only the extra initialization cost now, but also the extra cost of winding everything down and having a graceful shutdown. Now what's incredible is that we could literally just go ahead and go to any like SHA-256 hashing algorithm or implementation, feed in 10 Bakshi and just append this one string to it, and suddenly you would have it start off with a certain number of zeros. More than 36 bits in the beginning would start with 0. That is truly incredible. What I quickly do want to do is I want to modify the code and just show you what happens if we go down to 1 GPU. See, it's only 1 GPU, and we're going to reduce the difficulty to like 3 just so that we can speed this up a little. And if you take a look, what happens is if I go ahead and compile this, and if I go ahead and run this code, watch this. It's going to find a solution, and, well, maybe that was a bit too simple. But I'll just bring it down to like 4. This will take a second. And then go ahead and comment out this line of code over here. And watch this. What's really fascinating about this, is that the scaling is nearly linear. Well, see, this problem is way too... There we go. See? Finally, I was able to demonstrate the linear scaling. You see, what's amazing is that just a single GPU is reaching about 2 billion hashes per second. And if we go ahead and take 4 GPUs worth, which is like 8.4 billion, and if we divide this by 4, we can notice that it's 2.1 billion hashes per second. So this specific use case is such that because there's no communication across GPUs and things like that, it scales linearly. It's absolutely incredible the way this technology works, and it's only possible thanks to the power of CUDA. And so that brings us to the end of today's tutorial. I really do hope you enjoyed, and I hope this was insightful and helped you learn a little bit more about the world of CUDA, how it works, and how some of the algorithms behind the world of blockchain work as well. Now, of course, if you do like this kind of content, please do make sure you subscribe to the channel, as it really does help out a lot. And of course, do turn on notifications, and that way you're actually notified whenever I go ahead and release new content. And with that, please do feel free to leave any questions or suggestions you have down in the comments below, or reach out to me on social media, and I would love to answer them. And the code is on GitHub and in the description. All right, thank you very much, everybody. Goodbye.